Ever wonder what really happens when you hit run on your code? It's not magic. It's a meticulously engineered journey. Understanding this isn't just theory. It makes you a better debugger, a more efficient coder, and helps you choose the right tool for the job. It's the secret language beneath the code you write. By the end of this video, you'll demystify the journey your code takes from plain text to lightning-fast execution. Chapter 1. The raw text and the tokenizer, lexing. When you write print, hello world, in Python or console.log, hello, in JavaScript, to you, it's a clear instruction. But to your computer, it's just a raw sequence of characters, a string of bytes. It doesn't inherently understand print, console, or even what a function call is. It's like handing a complex recipe written in French to someone who only speaks English. The very first step in making sense of this is called lexical analysis, or tokenizing. Imagine a meticulous librarian scanning your code. It doesn't understand the full meaning yet, but it groups characters into meaningful units called tokens. So print becomes an identifier token, becomes an parent token, and hello becomes a string underscore literal. This process discards white space and comments, simplifying the raw input. Chapter 2. Parsing and abstract syntax trees, ASTs. With our neat list of tokens, the next phase is syntax analysis, handled by the parser. This is where the language's grammar rules come into play. Think of it like checking if your tokens form a grammatically correct sentence. For example, 10 plus would be syntactically invalid because it's missing an operand. The parser ensures your code adheres to the language's structure, preventing nonsensical statements from proceeding. If the syntax is valid, the parser constructs an abstract syntax tree, or AST. This isn't just a list. It's a hierarchical tree structure representing the meaning and relationships within your code, abstracting away the exact syntax. An AST is crucial because it provides a universal representation that compilers, interpreters, and even code analysis tools like linters can understand and manipulate, regardless of the original source code's formatting. Chapter 3. Interpretation versus compilation. Two paths to execution. Now that your code is a beautiful, structured AST, how does the computer actually run it? This is where programming languages take one of two main paths, interpretation or compilation. Each path has significant implications for your code's performance, portability, and even how you develop software. It's a fundamental design choice that shapes the very nature of a language. So far, we've seen how your code gets structured in the two main ways it can run. But what if there was a way to get the best of both worlds? The portability of interpretation and the raw speed of compilation. This is where things get really clever, leading us to a revolution in language design with bytecode and JIT. An interpreter reads your AST, or even the tokens directly, and executes the instructions line by line, on the fly. Think of it like a chef following a recipe step by step as they read it. Languages like Python, Ruby, and older JavaScript implementations are primarily interpreted. This offers incredible flexibility and portability. The same code can run on any system that has an interpreter for that language, without needing a separate build step. However, this often comes at a performance cost, as each instruction must be processed at runtime. In contrast, a compiler takes your entire source code, or its AST, and translates it into a lower-level language before execution, typically machine code specific to your CPU architecture. Languages like C++, Rust, and Go are compiled. This pre-translation step means the computer doesn't need to interpret instructions on the fly. It simply executes the already translated machine code. This results in much faster execution speeds, often leveraging hardware capabilities directly. The downside? You need to compile your code for each target platform, creating platform-specific executables. Chapter 4. The rise of bytecode and virtual machines. The limitations of pure interpretation, slow, and pure compilation, platform-dependent, led to a brilliant hybrid approach, bytecode. Instead of compiling directly to machine code, many modern languages like Java, Python, and C# compile their AST into an intermediate, platform-agnostic format called bytecode. This bytecode is a low-level, optimized set of instructions, but it's not tied to a specific CPU. It's like a universal assembly language that no real CPU actually understands. This bytecode isn't executed by your CPU directly. Instead, it runs on a virtual machine, VM. Think of a VM as a software computer that understands and executes bytecode instructions. The Java Virtual Machine, JVM, is the most famous example, allowing Java code to achieve its write once, run anywhere promise. Python has its own VM, and C# runs on the .NET Common Language runtime. The VM acts as an abstraction layer, translating bytecode into native machine instructions at runtime, making the code portable across diverse hardware. Chapter 5. Just-in-time JIT compilation, the speed boost. While bytecode and VMs offer fantastic portability, they can still be slower than natively compiled code because the VM still has to interpret or translate the bytecode during execution. This performance gap was a significant challenge, especially for web-based languages like JavaScript. Continuously interpreting the same bytecode over and over again for frequently executed functions is inefficient. This problem led to the invention of just-in-time JIT compilation. A JIT compiler is a crucial component within many modern VMs. It observes your running bytecode. If it identifies a piece of code that is executed very frequently, a hotspot like a loop or a frequently called function, it doesn't just interpret it repeatedly. Instead, the JIT compiles that specific hotspot directly into highly optimized machine code at runtime. This machine code is then cached and reused for subsequent executions, dramatically speeding up performance without losing the initial portability of bytecode. JIT compilers are incredibly sophisticated. They profile code, perform aggressive optimizations like inlining and dead code elimination, and can even de-optimize if runtime assumptions change. This dynamic optimization is why modern JavaScript engines like Chrome's V8 or Node.js are so fast, often achieving performance close to natively compiled languages, despite JavaScript being an interpreted language initially. It's the ultimate blend of flexibility and raw speed, a testament to decades of compiler research. Let's recap. We started with lexical analysis, turning raw text into meaningful tokens. Then, parsing structured these tokens into an abstract syntax tree, AST, representing your code's true meaning. We explored interpretation, line-by-line execution, and compilation, pre-translation to machine code, each with its trade-offs. Finally, we saw how bytecode and virtual machines combine portability, and how just-in-time JIT compilation dynamically optimizes hot code for peak performance. The key takeaways: understanding these layers helps you debug more effectively and appreciate language design choices. The choice of execution model, interpreted, compiled, or hybrid, significantly impacts a language's performance and flexibility. Modern programming languages leverage sophisticated techniques like JIT to deliver both developer convenience and blazing fast execution. If you found this deep dive valuable, hit subscribe and the notification bell to keep learning with us. Drop a comment below and tell us which programming language's internals you find most fascinating.